Thanks everyone for joining me today to listen to this short webinar about the modeling of discontinuous fiber composites with improved accuracy. As Srinivas said, my name is Kurt Danielson, and I work as the Business Development Manager for Extreme Engineering, a subsidiary of MSC Software. So just a little bit about the team, and then we'll talk briefly about Digimat, some background around material modeling, and then get into how Digimat can help you improve the accuracy of your finite element analysis of discontinuous fiber composites. So as Srinivas mentioned briefly, I work for Extreme Engineering, which is an MSC software company. We are an independent subsidiary, which means that we were an independent company until September of 2012, at which point we were purchased by MSC, and we now work as a kind of a smaller entity inside of MSC. That smaller entity is focused 100% on material modeling, so improving the accuracy of modeling materials, focused really completely around composite materials. So we deal with a variety of different composite material types, everything from discontinuous fiber composites, short and long, like we're going to talk about today, continuous fiber composites, as well as discontinuous fiber composites as well, and some even more exotic composite materials such as concrete or metal matrix composites. We look at a variety of different physical phenomena for those materials, focusing mostly on mechanical and thermomechanical analysis, since that's where most of the CAE action is happening these days, and then really trying to take into account the variety of different manufacturing processes that these materials are used with, and take the considerations from those manufacturing processes and bring them into the finite element analysis so that you can get a better prediction of your overall part performance for whatever you may be concerned about, whether that's stiffness, strength, or something more advanced like fatigue or creep. So in addition to being a material modeling company, we are also a software company, and we produce a product called Digimat. Digimat is the premier material modeling software. It's a set of two different groups of products. There's a set of tools that allow you to do very detailed finite element analysis and really solve a really wide variety of different problems for a wide variety of different materials. And that's that top set of icons you see there in the window displayed. And then in addition, now we've developed a couple of sets of vertical solutions, and we'll have more coming later this year, so stay tuned, and we'll talk about those as well. But those are really more focused around solving individual problems. They're more workflow-oriented with integrated environments to really get you a fast, robust, easy solution for the more specific and popular problems that our customers are solving. So now we've talked about Digimat and a little bit of the motivation why our customers are using Digimat. So this is an excerpt from an article that was written by one of our customers over in the Ford Interiors group. And essentially the motivations to use Digimat are similar to the motivations that all of you started using CA to begin with. And that's really that by using Digimat, you can design better parts, so lighter weight, 10 to 20% mass reduction compared to traditional finite element methods, which leads to more material cost reduction, which also, by doing better analysis and more accurate analysis, you'd have less likelihood that you're going to have those, late-stage surprises after the part has been tooled. That means you have to go back and do those costly late tooling changes. So it also reduces the risk in your overall design and release process. So that's a little about the motivations for why people are using Digimat. And who are our customers that are then motivated to use Digimat? So we have a variety of customers across a number of different industries, from material suppliers who we typically have quite a close partnership with, into the automotive sector in both the OEMs and Tier 1s. We as well have a number of customers in a variety of different aerospace sectors, as well as electronics and electrical equipment. We also have a growing customer base in the medical device industry. So kind of a wide variety of customers solving a wide variety of problems, but with one common element amongst all of them, and the fact that they're dealing with composite materials, and a lot of them with the discontinuous fiber composites that we're going to talk more about here in a moment. So now that we've talked a little bit about who we are and what we do, let's talk a little bit about some background about modeling fiber-reinforced plastics or discontinuous composites, just to make sure that we're all on the same page here. And I apologize for any of you that this is a bit elementary for. So if we start with the really most basic part we can think of, that part would be just a really simple flat plate. And if we were to take that part and we were to study a piece of material at the very center of that plate, the way that we might study that piece of material is that we could cut a couple of dumbbells where that piece of material is at the center of the dumbbell from the plate, and then we could test those dumbbells in a tensile testing machine. And what you would see is something like what I've got shown here. So in the case where we test the material so that we're loading it in the flow direction of how the part was manufactured, we're going to see something like that gray curve there. So it's going to be very stiff in the beginning, and then it's going to fail at a relatively high stress, low strain, so a relatively brittle performance. In the second scenario, where now we're going to load the material transverse to the direction of how that part was injection molded, so the flow direction during the injection molded, we're going to see a response that looks more similar to the red curve there, where the material is going to be less stiff in the beginning, and then it's going to go into plasticity much sooner. It's going to be much more ductile, so you're going to have a much higher strain and lower stress at failure. So very different material response for those two different loading scenarios. And really what we're seeing there is the effect of the local fiber orientation on the material. The traditional way to deal with this kind of variety of different performances that you might get out of the same piece of material is to use an isotropic material model, where you take the two different curves and you use some type of blending algorithm, or maybe you just have one curve and you add a knockdown factor, and you really say, well, I know the material behaves somewhere between A and B, so I'm just going to assume that it's C, and that'll get me pretty close. And that approach works quite well for matching global stiffness or one single load case. But when you have multiple load cases, or you're making big changes between parts, that approach becomes quite difficult. In addition, it's not an easy approach to deal with if you're trying to really optimize your parts or be predictive, avoid those late stage tooling changes or those surprises at the end. And as you can see, you can have very different stress and strain at failure. So modeling things like failure, impact, and fatigue is also quite different with an isotropic approach. So that's really the background around why Digimat was created. So the way that Digimat handles that issue is using mean-filled homogenization. And this is really the engine behind Digimat that allows us to be so accurate in our analysis of these discontinuous fiber composites. So what we do is we build our material models at a level below the traditional composite level that most people are modeling in finite element analysis. So we have a description in our material model. We have a description of the matrix, so a stress strain curve for the matrix, if you will. We have a description of the fibers, and then we have a description of the local microstructure. And what that means is that we're going to have a description of what the fiber orientations are, how aligned they are, how random they are, in what direction. We're going to have a description of how long the fibers are, so the aspect ratio. And we're also going to have a description of how many fibers there are for how much plastic. So what's the volume fraction of fibers relative to the plastic. From there, we can homogenize all those different properties together to predict what the composite response is. So we can go back to our input and we can vary that fiber orientation, and we can predict the composite response as you see in the top curve, where the fibers are very aligned in the direction of flow, so similar to the gray curve on the last slide, to the scenario where the bottom curve where the fibers are very transverse to the direction of loading, and then kind of anywhere in between there, where you have randomly aligned fibers, or you have partially aligned fibers, or just really a wide variety of scenarios there. And it's more complicated and more accurate than just blending between multiple curves. This is really using the base material properties to be predictive of how the composite is going to respond. We can also do that for discontinuous and continuous fiber composites, for stiffness and failure. We can also add in temperature dependence to these materials, including a CTE that varies as a function of your local fiber orientation, something that's very important to a lot of our customers in the electronics industry. And we can add in strain rate dependence, something that is very important to people doing impact modeling. So you take into account the fact that these materials are going to be stiffer the faster you pull on them. At the end of the day, we can take all of this, and I'll show this in a little later in the presentation. We can take all this material and we can tune it to your material test data so that you can have a very accurate material model that then will allow you to be predictive at the part level. So instead of having to design your parts and go back and tune your knockdown factor, you can do it all up front and then really predict how your part's going to perform even before you make it. So that's a little bit about the magic behind Digimat, if you will, or the science behind Digimat. If we look at how Digimat works in a finite element analysis, it looks something like this. So in the traditional finite element world where people are working without a tool like Digimat, what they generally do is they take some information coming from the material supplier. That could be a data sheet. It could be a stress strain curve. They then bring that information in their finite element analysis through a standard isotropic material card. Maybe that's linear or nonlinear. And then they run their finite element analysis on that material and try and predict what the part performance is going to be. At the same time, typically they have people working inside their group doing processing simulation. And this could be compression molding, this could be injection molding. And they're trying to maximize the output on these parts, so make it easier to manufacture, try and reduce the warpage. But there's a lot of other information in that simulation that isn't being taken into consideration in the finite element analysis that's very valuable, namely the fiber orientations. So what Digimat allows you to do is it allows you to take the information coming from your material supplier, so your stress strain curves. You can then build a advanced nonlinear anisotropic material model, so one that takes into account the local fiber orientations. You can then take the information coming from your injection molding simulation and map that over to your structural analysis. And this step is important here because that means that you don't have to have the same mesh in your injection molding simulation as you do in your structural analysis. You know, typically you have very different mesh parameters in your injection molding simulation versus your structural analysis. So you can map that information over. You can then bring that all into your finite element analysis to get a more accurate prediction of how your part behaves. So one of the most important things about this approach is that it allows you to take things like weld lines automatically into consideration. So the areas where you have these weld lines, you'll have these little balls of randomly aligned fibers from the two flow fronts meeting, and in those areas you'll see this reduction in stiffness and reduction in strength that typically comes along with a weld line. All of this work can be done inside of one of those vertical solutions that I mentioned before. That vertical solution is called Digimat-RP. It stands for Digimat Reinforced Plastics, and it's really a very fast and easy way for our customers to be able to work with inside of one GUI interface in order to do all of the different tasks that they need in order to bring a Digimat material into their finite element analysis. Any of you who've had any experience with Digimat before, this is a brand new product for us, and I think something that's very interesting for increasing the productivity for our customers using Digimat. So just a quick case study here, and then we'll talk a little bit more about how the technology can work with Nastran, and then get into another case study to finish things off. So this is a case study done with Trelleborg. They're a vibration solution manufacturer, amongst other things. And what they were trying to do was to replace a steel engine mount bracket with a fiber reinforced plastic material in order to reduce the cost and reduce the weight of the material. And they decided to use Digimat in that design process in order to more accurately predict how the part was going to perform so that they could design a better and lighter part. The material they chose for that analysis is a PA66 nylon reinforced with glass fibers. And you can see from the chart below that this is quite a complex material to deal with. From the three different colors of curves, or three different groups of curves, you see that the material has a variety of stiffnesses and strengths depending on what the local fiber orientation is. In addition, you can see from the inside each one of those groups that the faster you pull on that material, the more stiff it's going to behave, which means that it has a strain rate dependence. So this is a relatively complex material to deal with, and so they decided to use Digimat in the design process in order to take all of those things into consideration at once. You can see the results from the validation step that they did after the design process here on the screen. So using Digimat in the design process, they were able to get a 40% weight reduction, which led to a 15% cost reduction in the manufacturing of the part. In addition, they were able to get very accurate analysis results from their FEA. So in the graph, what you see is a comparison between the validation test results with an isotropic approach, and this is an approach where they're really just pulling the material's properties directly from their material supplier, and then with the Digimat approach. And so what you see there is that the Digimat approach gives you a very accurate prediction of what the force versus deflection curve should look like, so what the stiffness of the part should be. And in addition, what you see below is that using one of Digimat's custom failure indicators, which monitors the material at a level below the composite. So looking at the matrix and the fibers more individually, they were able to get a very accurate prediction of where they should expect to see failure in this part. And while the stiffness may have been approachable with an isotropic model, predicting where and when the failure would occur is something that is extremely difficult with an isotropic approach, and someplace where Digimat really has a lot of added value. So that's a little more of a demonstration about why people are using Digimat. So let's talk a little bit more about what the Digimat process looks like and how you might go about adding one of these Digimat material models to your analysis. So I showed you the workflow for how the Digimat fits into the finite element analysis, but a common question from people new with Digimat is, where do I get this type of a material model from? And we've got two different places that you can work with to get your material model from. The first one is from our Digimat-MX database. So with the installation of Digimat, you get access to this material database, and this material database is not just a database, which we'll get into a second here, but in that database, we have 112 different material grades with a variety of different matrix types, so everything from your different nylons to polypropylene, PBT, PEEK, polyoxylene, methylene, as well as glass and carbon fiber composites. And one of the neatest things inside here is so a variety of these material models are coming from a bunch of our different material supplier partners, so kind of some of the main players in this industry here. But in addition, we also have this Digimat generic material model database. And that generic material model database, along with the suppliers, the material models from the grades, gives you this ability to take these material models out of Digimat-MX and be up and running with the Digimat material very quick and very easily. This is going to give you a big increase in the accuracy of results, even if you're using one of our generic material models, because you're going to really capture that first order effect of the local fiber orientation. So you're going to be able to very quickly increase the accuracy of your analysis relative to your isotropic approach. And this is going to work quite well for stiffness. But if you want to increase the accuracy a little bit further and you want to start to capture things like failure, or you want to really bring that accuracy level down to the 3 to 5% that we like to see with metal parts in a finite element analysis, then you need to use our more detailed or quantitative approach. And in that approach, you can take one of those generic material models, you can pull it out of the database, you can bring your test data coming from either your material supplier or maybe you've had some material testing done on your own, and you can bring that inside of Digimat-MX, and in there we have an automatic reverse engineering tool that will tune your Digimat material model to more closely match your test data. In addition, you can also tune one of our custom failure indicators in there to be able to predict the failure response of your material. So in that way, you can take this material model, you can tune it to your exact test data, so you have a material model that matches your exact formulation of composite material, stiffness, and failure. And this will allow you to be predictive then when you go and bring your analysis to the part level. So here's another case study example. This is a case study done with Schneider Electric on an electrical bracket that they were looking at manufacturing with a glass-filled PBT. So what you see here is a couple of different curves. You've got the red curve, which is their test results for one loading scenario. You've got the black curve, which was their isotropic approach that they were using before Digimat, so really not giving a very accurate picture of stiffness at all. And then you've got your two other approaches, which are labeled here as the semi-quantitative and quantitative approach. And what you see is that the semi-quantitative approach gives them a big increase in accuracy right away by taking into account those local fiber orientations, and that's really pulling the material model right from the database. And then the quantitative approach is going to bring them even closer and a much higher level of accuracy by tuning that material model to some material test data that they had before this analysis. So just a couple more comments about using Digimat with Nastran, and then we'll wrap things up with more and more case study that really talks about using Digimat for an impact analysis and predicting failure. So currently, Digimat interfaces with both Nastran Solutions 400 and Solutions 700. So that allows you to do things like NVH analysis, static analysis, dynamic, high strain rate, or impact problems. We can handle both nonlinear implicit as well as dynamic explicit analysis. And a couple notes about those Nastran solutions for some of our customers out there who are maybe more familiar with the classic Nastran solution. So Nastran Solution 400 is MSC's newest linear and nonlinear Nastran solution. It's comparable. It has comparable solutions to the Nastran 100 solution sequences, so it kind of meets a wide variety of needs. You can capture all your Solution 100 sequences that you're used to using, as well as take into account a wide variety of different nonlinearities, such as material nonlinearity, looking at elastic, elastoplastic, hyperelastic, composite materials, time dependence, plasticity, and failure analysis. You can look at large deformations and strains, take contact into consideration, and do multi-physics problems inside of Nastran Solution 400. So it's really a very capable solution that gives you a wide variety of different problems that you can solve. And one of the big advantages of it is that it interfaces with Digimat, or big advantages in this topic that we're discussing here. In addition to interfacing with Nastran Solution 400, we also interface with Nastran Solution 700. Solution 700 is Nastran's transient dynamic solution for high-speed events, so really an explicit solver aimed at modeling high-speed dynamic crash events and other dynamic events happening inside the variety of industries we work with. We can look at both structural as well as fluid structural interaction, and there's a lot of variety for ways that you can tune this solver to match your specific problems. So in that way, by using Digimat with Nastran, we have two different solution types that work well with Digimat that can solve just about any problem that you're looking to solve in the finite element world. So a case study to demonstrate how that might work, or what kind of accuracy you can expect out of Solution 400 for our Solution 100 users out there. This is a short case study we did with a Renault front-end carrier, which is polypropylene reinforced with glass fibers. In this case, in the first step, we wanted to compare Solution 103 to Solution 400. So really looking at a modal analysis just to make sure that as we move it from one solution type to the next solution type, we can still expect the same level of accuracy and the same type of results we did with our 100 solution that's really been our legacy solution. So you can see here from the chart on the right that we see a good correlation between the various eigenmodes for these two different solution types. And in addition, when we add Digimat into Nastran Solution 400 and we take into account that variety of local fiber orientations, we see an increase in the accuracy of the modal analysis. So we start to see that those modal frequencies shift. The part is actually a little softer than we expected because now we have these areas of randomly aligned fibers, and you get a more accurate solution using Digimat plus Solution 400 relative to the traditional 103 approach. So one more case study here, and then I'm going to wrap things up and then open up for questions. So this case study is a metal to plastic design comparison, really looking at stiffness and failure prediction for an impact scenario. So in this case, case study was done by Faurecia with Solvay. Solvay is one of our material supplier partners, and they were trying to take a reference seat, which was made from all steel, and convert that into a nylon reinforced with 30% glass fiber steel pan. Using Digimat in the design process, they were able to get a 50% reduction in the number of parts and a 40% reduction in the overall weight with the same functionality, going from the steel seat pan over to the nylon reinforced with glass fiber seat pan. So on the next page here, what we see is the results from the injection molding simulation. And what you see is that the fiber orientations vary, where you have the areas that are blue, which is the more randomly on fibers, the areas which are red, which are the more transversely or highly aligned fibers. And you have kind of a wide variety of those fiber orientation scenarios happening across the part. And this is really a good indication that a tool like Digimat is going to be very powerful with this type of analysis, because just as those fiber orientations vary through the part, so will the material properties. So this is a description of what the validation scenario was for this material. So it was a 3-point bending impact test where they were trying to capture not just the force versus deflection curve, but as well as the failure mechanism of the part. And you can see from the chart on the left here that they were able to capture that quite well. what we're going to do is we're going to compare a couple of different analysis approaches at 3 different time steps right before some major failure events in the material. So in the first case, we'll look just before you had a rib buckling. That rib buckling then leads to a rib failure, and then a final failure evolution that causes the ultimate failure of the part. The 3 different analysis approaches that we're going to discuss are described up at the top there. So you see in the first approach on the left, this is really, we refer to as the ISO 527 approach. This is taking the data from your material supplier and just dropping it right into your finite element analysis. In the second approach, you apply a knockdown factor to try and match the global stiffness of the part. So you take that material data coming from your material supplier and you reduce it by some factor to match your global stiffness. And then in the third approach, that's Solvay's MMI approach, or really Digimat in the hands of Solvay. So in the first case, at the first scenario, so your loading has really just started to happen and just before we have that stiffness reduction. In the first case with the ISO 527, your very stiff isotropic material model, you have a failure that happens too early and in the wrong place at the wrong direction. For the scaled approach, you don't have that failure, and in the Digimat scenario, you don't have that failure. And if we look at the local fiber orientations there, we can see why. In that area, we have, you can see we've got a relatively blue color, which is telling us that the local fiber orientations are quite randomly aligned there. And that means that we're going to have a much softer material response. So this first case where the material model is quite stiff is not going to be able to capture that. As we move further along in the analysis, now in the first case, that initial failure that we had that shouldn't have happened has continued to progress and has moved transversely along the part. We have started to see the rib failure, or the rib buckling that we expected to see, so that's very positive for this first isotropic approach, but we do have this other failure that we didn't mean to happen. In the second approach, we have not had the failure that we should expect to see on this softer isotropic model. And in the third approach with Digimat, we have captured that failure. Once again, if we go and look over at the fiber orientations, we can see why this is happening. So what you see is that along that rib, we have this very orange-colored group of fibers, and those fibers are aligned in the direction of loading. So they're going to be very, very stiff relative to the last scenario that we're looking at. So that's why you can capture this failure in both the isotropic approach, where you have a very stiff material model all around, and the Digimat approach. Because in the Digimat model, you're going to have soft fibers where they're actually soft, or soft material where it's actually soft, and stiff material where it's actually stiff. In the final scenario, now we're about to have a final failure of the part. If we look at the first approach, the isotropic approach, because of that initial material, or that initial failure we had, the transverse failure, now our failure is progressing in the wrong direction, so moving away from the rib. So we're not going to be able to accurately predict the failure mode or the failure amount of the part, force-it failure of the part. In the scaled approach, now we finally started to have failure at the rib, but it's too late in the analysis. And in the Digimat approach, we had failure happen in the right place at the right time, and now it's progressing in the right direction along that rib to match what we actually saw in the test results or experimental results. So at the end of the day, if you compare Digimat to the 2 different isotropic approaches, it's the only one that was able to capture all of the different failure events. In addition, it's the only one that's going to give you an accurate prediction of how the part's going to perform for both stiffness and for failure. Thank you very much for your attention today, and at that point, I will open things up for questions.